Modules and ports. We're going to enter into the Verilog HDL language. Now we'll start with the basics of the Verilog. In this tutorial, we're going to discuss modules and ports of the Verilog HDL. Now we've discussed the design methodologies in our previous tutorial. We now relate these hierarchical modeling concepts to Verilog. Verilog provides the concept of a module. A module is the basic building block in Verilog. A module can be an element or a collection of lower-level design blocks. Normally, elements are grouped into modules to provide common functionality that is used at many places in the design. You know, a module provides the necessary functionality to the higher-level block through its port interface, that is, inputs and outputs, but hides the internal implementation. Now, this allows the designer to modify modules' internals without affecting the rest of the design. Let's consider the same ripple carry counter, which we discussed earlier. In ripple carry counter, T flip-flop and D flip-flop are examples of modules. In Verilog, a module is declared by the keyword module. A corresponding keyword, N-module, must appear at the end of the module definition. Each module must have a module name, which is the identifier for the module, and a module terminal list, which describes the input and output terminals of the module. This is how it looks. It starts with the keyword module and then followed by the module name, which is then followed by terminal list that are enclosed in small brackets. Now, in the next few lines, we'll have the module internals and finally ends with the N module. Now, we can define the T flip-flop as a module. It looks like this. Here, we've given the module name as T flip-flop, and module terminal list has inputs and outputs of T flip-flop, which are Q, reset, and clock. Here we had to remember that module names shouldn't start with numbers or special characters, and we should not use symbols within the module name. Finally, we should end up with the N module. The internals of the module are not visible to the environment. I will discuss about module internals in forthcoming tutorials. Next up, let's talk about ports. Not the kind that you drink, however. Ports provide the interface by which a module can communicate with its environment. For example, the input or output pins of an IC chip are in its ports. We can interact with the module only through its ports. We know that the internals of the module are not visible to the environment. This provides a very powerful flexibility to the designer. We can change the internals of the module without affecting the environment as long as the interface is not modified. Ports are also referred to as terminals. Now, we've got a list of ports. That is, a module definition contains an optional list of ports. If the module does not exchange any signals with the environment, well, then there are no ports in the list. Let's consider a 4-bit full adder. Now, here we have the diagram for the input and output ports. We'll name this module as full add 4. The module full add 4 takes inputs on ports A, B, and carry in, and produces an output on ports sum and carry out. Thus, module full add 4 performs an addition for its environment. Now, this is how it looks with the module name, inputs, and outputs. Now we'll see how to declare these inputs and output ports. All ports in the list of ports must be declared in the module. Now, we've got 3 types of ports. They are input, output, and bidirectional port. We have a keyword for each type. For input port, the keyword is input. For output, as you can guess, it is output. And for bidirectional, well, that's in-out. Each port in the port list is defined as input, output, or in-out based on the direction of the port signal. Thus, we shall give the port declarations the example of the full add 4, and it's like this. As usual, we start with the keyword module, and then module name, which we named full add 4, and then inputs and outputs are enclosed in brackets. Now we know that A, B, and carry in are inputs, and sum and carry out are outputs. But we need to mention them in the coding, that which are inputs and which are outputs. For that, we should specify along with the keywords input and output. So we declare cout as output cout. Since we're going to perform 4-bit adder, inputs contain 4 bits, and output sum will also contain 4 bits. So we specify the 4 bits as 3 is to 0, which means 0, 1, 2, and 3 bits. Now we declare the output sum as output 3 is to 0 sum. Similarly, we specify for inputs. And then we know module internals will be present. And finally, ending the code with end module. Note that all port declarations are entirely declared as wire in Verilog. Thus, if a port is intended to be a wire, it is enough to declare it as output, input, or in-out. Input or in-out ports are normally declared as wires. If output ports hold their value, they must be declared as reg. For example, let's consider the D flip-flop. In the definition of D flip-flop, if we want the output Q to retain its value until the next clock edge, we should declare it as output reg Q. And here we have the port declaration for DFF. For D flip-flop, we know that D, clock, and reset are inputs, and Q is output. Now, since we're using only 1 bit for inputs and outputs, we will declare them along with the keyword input and output. We want the output Q to retain its value until the next clock edge. We declare it as reg Q. Here, note that ports of the type inputs and in-out cannot be declared as reg because reg variables store values, and input ports should not store values, but simply reflect the changes in the external signals they are connected to. Note that the module full add for, which we have seen before, can be declared using ANSI C style syntax to specify the ports of the module. Each declared port provides the complete information about the port. Now here we have the alternate syntax. This syntax avoids the repetition of naming the ports in both the module definition statement and the module port list definitions. If a port is declared but no data type is specified, then, under specific circumstances, the signal will default to a wire data type. Now, to be more clear, normally we are writing the inputs and outputs twice, that is, at the module terminal list and after the terminal list along with the keywords input and output. But instead of writing twice, we can directly specify or declare the inputs and outputs along with keywords at the module terminal itself, such as this. Right then, I hope you've got a clearer idea about modules and ports. In our next tutorial, we'll deal with data types.